Thank you. Well, as you can tell from the title, I'm not really following the salt feedback theme that was the original idea for this series of webinars. It's not completely unrelated to those interests, because part of the issues related to climate change and the AMOC are sources of fresh water and their potential for inhibiting deep convection and affecting overturning circulation. One source of those fresh waters are meltwaters coming from Greenland glaciers. So we're a bit upstream from the deep convection regions, but this really deals with the issue of exchange between the relatively warm shelf waters of Atlantic origin and the base of the Greenland fjords. So this is work I've been doing with Becca Jackson and Fiamma Stranio. I'm going to, oh, there we go. So just a little bit of background. This is a map of wind speed taken from a reanalysis product. This is a different fjord than the one I'm going to focus on, but the main point is you see really strong winds in excess of 20 meters per second along the downslope portion of Greenland, and these correspond to the passage of low pressure systems between Greenland and Iceland. So this panel on the right is sea level pressure. The events are quite strong, over 20 meters per second. They last 1 or 2 days. You might see between 5 and 10 events per year in a given fjord, and I don't show it here, but the temperatures in the atmosphere are very cold. So these are quite strong episodic forcing events. This is very slow to turn pages here. I'm not sure why. There we go. So I'm going to look at this from a very idealized perspective with some numerical model calculations. We're going to include some data at the end and a little bit of theory in the middle. So the fjord for which we have data from Fiamma and Becca's work is Surmillik Fjord. This is a map of it here. That square is the location of a mooring from which I'm going to show some data later on. There's a weather station here that's measuring along fjord winds, and then there's the area interim data point out here, which we're going to talk about along shelf winds. This is my model version of a fjord. It's periodic in this direction. There's a long, narrow channel here that's a fjord. It's a flat bottom, and I'm starting at rest with an approximation of a 2-layer system. So this is intended to represent winter-like conditions. This curve on the right, this solid line, that's a profile of potential density as a function of depth taken from that mooring. And you see it's approximately a 2-layer system with a transition at about 150 meters depth. So my model that I'm going to talk about the most is a 100-kilometer long fjord. It's 6.5 kilometers wide, 500 meters deep. There's a 2-layer system that has a transition at 150 meters. The stratification is such that the gravity wave speed is just about 1 meter per second, and the deformation radius is about 8 kilometers. So these parameters are roughly in accord with Surmillik Fjord. For most of the model calculations, I'm going to start with this 2-layer system at rest. I turn the wind on. It's uniform in space, and I'm going to hold it constant in time for 3 days. It's not intended to represent a real Katabatic wind event, particularly the time dependence, but it's useful for comparing with some of the theories I'm going to talk about. So I'm using the MIT GCM. Grid spacing for most of these calculations is 250 meters. I've done some at 125. There's 20 levels in the vertical. I employ a KPP mixing and a Smagorinsky horizontal viscosity. Okay, this is just an example of the exchange that you get at the fjord mouth. So this upper left panel, this is depth, and this is the meridional velocity integrated across the fjord as a function of depth and time. So the wind is constant for all this time. You see we're spinning up this negative velocity that's flowing out of the fjord. In the deep, there's a weaker but deeper inflowing velocity. So these two are close to integrating to zero. So the net exchange is primarily baroclinic. This white line is the interface between the fresh upper layer and the saltier deep layer. It deepens slightly over the time period. So if I just pick out the maximum depth, the depth average transport as a function of time in this upper fresh layer, this solid line on the right is what you get. So it increases almost linearly up to about a day, and then it abruptly turns around and starts decreasing, and after 3 days, there's no exchange. This dashed line is what comes from this simple two-layer theory of farmers down here, and it agrees surprisingly well. Spins up almost linearly. After about 1 day, it turns around and goes back to 0, and then in the theory, it remains motionless. So at this end state, you've got wind blowing, trying to blow the water out the fjord, and that has set up a pressure gradient that exactly opposes the wind. So there's no acceleration of the flow, and it remains at 0. This is a two-layer theory. From Farmer, it ignores rotation. I'm presenting here the inviscid version. He's got interfacial friction, but I'm not considering that here. And if you look at the details of this, you see the flow spins up on this time scale of d, which is the meridional extent of the fjord divided by the gravity wave speed, which is just about 1 day for these calculations. And that's also coincidentally about the time length of these synoptic wind events. So the spin up is an equilibrium time scale is comparable to the time scale of the synoptic winds. So that's an inviscid theory, but at some point I think we can expect friction might become important because fjords are fairly narrow. So I'm going to make an assumption here that I'll justify in a couple of slides. I'm going to say if the fjord is narrow enough that the balance is going to be between wind and friction. If the fjord is very wide, the Farmer model assumes the balance is between wind and a pressure gradient. So if I balance friction with wind forcing, and for this model I'm using the Smagorinsky viscosity, which depends on the deformation field or the strain field. So if I assume just a narrow boundary layer structure, it's going to be proportional to the horizontal velocity gradient, dv dx, and this is just a constant here. So if I assume dv dx scales as some maximum velocity at the middle of the channel divided by some boundary layer width delta, I can express A in terms of this. And then using the Farmer theory, I can express Vm, the velocity at the middle of the channel, as a function of the wind stress. So I combine those, I can get this expression for the boundary layer thickness delta. It's fairly complicated, depends on the wind to the 1/3 power, it depends on the stratification, depends on the length of the fjord. And then I can say, well, if the fjord's narrower than this boundary layer, half width of the fjord is narrower than delta, then the velocity isn't going to be able to reach this maximum velocity. It's going to be something less. So I can then invert this, essentially put L in place of delta and solve for the velocity, and I get this expression over here. So the maximum velocity is going to be less than this inviscid theory if the half width of the fjord is less than delta. And again, this is a fairly complicated expression. So now I'm going to justify that assumption. I've run a series of calculations which the wind forcing is the same, the stratification is the same. I've just varied the half width of the fjord, delta. It goes from very nearly 0, very narrow, to, I'm sorry, that here L is very narrow, delta is the same, to very wide, so 10 or 12 times this boundary layer width. And what I'm plotting here are the relative magnitudes of the 3 important terms that are balancing the wind. In this presentation, everything's normalized by the wind stress. So the wind would be 1, or -1 actually, because it's trying to blow out. The solid line is pressure. So for wide fjords, L much bigger than delta is pretty much pressure balancing wind, which is the Farmer model's assumption. As L gets smaller, the friction begins to become important and the pressure gets smaller. So we get down less than about 1 for L over delta. The balance is really between friction and wind, and pressure is not very important. That's the scaling, that's the assumption I use to derive that scaling. And then down here, this dashed line is the Coriolis term. It's small when the fjord is narrow. That's not surprising. But it remains small even when the fjord gets 2 or 3 times the deformation radius. I'm not plotting it in those coordinates here. But out here at the widest, it's between 2 and 3 deformation radii wide. You might expect Coriolis to become more important. But looking at the budgets, Coriolis remains small because I have Ekman transport from east to west in the surface, in the Ekman layer. But in the bottom part of the fresh layer, I've got a geostrophic flow going back to the east that nearly cancels out the Ekman transport. So the integral, the Coriolis term over that upper layer, is very nearly zero for all of these calculations. So I'm still going to do some more work and try to understand how general of a result that is. But empirically, that's what I'm finding for essentially all these calculations. It's never larger than about 10% of the wind stress. Okay, so this gives you a little justification for these two limits I'm looking at, the frictional limit and the inviscid limit, and the transition occurs on this length scale delta. So now I want to test these ideas over a wider range of model calculations. I've only shown you really one or a couple. So I've done a whole bunch of them now. There's, let's see, 1, 2, 3, 4, 5, 6, 7 sets of calculations in which I've varied either the wind stress or the change in salinity between the upper layer and the deep layer, or the thickness of the upper layer and the deep layer. Each symbol represents a different set of parameters, and then I've varied the half width of the fjord from 125 meters out to 10 kilometers. And each symbol represents a diagnosed maximum velocity. So if you remember the way things spun up, it started 0, went up to a maximum outflow velocity, and went back to 0. So in this diagnostic, I'm just picking off that maximum velocity, and I'm comparing it to, well, here I'm just plotting it. So it varies between about 2 centimeters a second down here, up to almost a meter a second up here. So there's quite a wide range. Now I want to test this with the theory. Over here on the right, I've normalized this maximum velocity by the Farmer theory, and I've normalized L by delta. So at this dashed line, we see most of the results cluster around 1. So that means the Farmer theory works reasonably well. These are all bunched up around 15. They really extend way out here, but I plotted them all here just so you can see the low end of the scale a little bit better. But they're all within, for the most part, about 80% of the inviscid theory, except for maybe a couple outliers. But as L over delta gets smaller than about 2, we can see all the calculations fall on a single line, and they depart from the Farmer theory, which is up here at 1, and they come all the way down here following this viscous theory, which is this solid line. So the basic balance is predicted. The inviscid limit for L greater than delta and the frictional limit for L less than delta seems to be supported by this wide range of calculations. So instead of just picking up the maximum velocity, another quantity you might be interested in is the total exchange between the fjord and the open ocean. So I'm not showing the theoretical representation of that here, but you can get it from that Farmer theory. So this is the diagnosed exchange in cubic meters from the model, and this is what's predicted by the theory. And if they agreed perfectly, they would fall along this line. Most of them do within a reasonable factor. For the open symbols, the closed symbols, the solid symbols are when L over delta is less than 1. So this is where we expect friction to become important, and indeed they do begin to fall below the theoretical prediction there. And this is just integrated over the time period for which the theory says you should arrive at an equilibrium state. So this 2D over C here. Now represent that as a percentage of the fresh water that was initially in the fjord. That's a quantity that's kind of interest. How much flushing can we achieve? So it varies. Again, the theory and the model, they cluster along this line that has a slope of 1, and they vary from only a few percent for very weak winds to around 10%. And this is per event. So we might expect that these kind of katabatic wind events are important for the freshwater and heat budgets of the fjords, because a single event can flush out on the order of 10% of the winds, and we get 5 or 10 of these things a year. Now Beckett tells me that the along slope winds are still more important when integrated over a whole season, but locally in time these events can be quite important. So that was all steady forcing, a longer duration than typically takes place. Now I want to compare with some observations with slightly more realistic forcing, although I'm still using the same rectangular flat bottom domain. Remember, this is the Sermilic Fjord. We're looking at data here. Now I'm going to show some wind taken from a MET station right on the border of the fjord. That's this thick solid line. And Becca has averaged these eight Katabatic wind events into one representative event. Now we've centered time at 0 at the peak. So it's about 1.3 newtons per meter squared, and its duration is on the order of a day. So weak winds, you get one of these big events, and then the winds go weak again. I'm going to show on the next page some winds from this station here. These are the along shelf winds. But for now, we'll just look at this one. And then this solid line is the velocity at 57 meters measured by that mooring. So negative means outflow. So shortly, about a day after the wind event, we see a peak outflow of about 30 centimeters per second. Then 2 days after the event, it reverses to an inflow of actually a bit stronger, almost 40 centimeters per second. And this continues to fluctuate in time. Okay, so now this is that wind forcing again. That's the same solid line we just looked at. This thin solid line is what I'm forcing the model with in the along fjord wind. Now this thick dashed line is the along shelf wind I mentioned that came from ERA interim analysis. About 2 days after these wind events, you actually see a little downwelling favorable along slope wind. So like a little barrier wind event. It's much weaker, but it's there a couple of days later. And you can't see it very well, but underneath that is a little thin dashed line that I'm forcing the model with an along slope wind, along shelf wind in the same way. On the right, this is the observed velocity of 57 meters, which we just saw on the previous page. And these thin lines are 2 model calculations. This one is with just the downfjord wind, so just this thin solid line. You see the same basic feature. The phases may be a little bit off, but you see a similar magnitude of about 30 centimeters per second outflow, lasts for about the same amount of time. And then we get this reversal and we get an inflow of about 30 centimeters per second. If I include that little downwelling favorable wind, I get this dashed line which persists the inflow, increases its magnitude and persists it in time a little bit. So, within the idealization of the model, both in terms of the forcing and the topography, this simple model seems to reproduce the basic characteristics of the observations. And then, relying on the model to test some of the theory and scaling ideas over a broader range of parameter space gives some confidence that the physics of those theoretical models may be relevant also for the actual fjord. So in summary, I didn't present evidence of this, but Katabatic winds are common along East Greenland fjords. I talked about some idealized numerical model calculations and simple theories that suggest 2 limits: a very narrow fjord where exchange is limited by friction, and what I think is, at least for Greenland, probably a more realistic parameter space where the exchange is well predicted by this linear non-rotating inviscid theory. And I think these events can be important to the freshwater and salt budgets, both of the shelf and of the fjord. So that's my 15 minutes of fame. I'm ready to take questions.